Another really good analysis technique that we don't actually use in class but can be used in larger laboratories is infrared spectra analysis. And it's another thing that we can be tested on in the exam, so let's have a quick look at it. Infrared radiation, if you think about it, it is just outside the visible spectra, the red end of the spectra, so that means it's going to have a longer wavelength and a shorter frequency than either UV, X-rays or gamma. But the interesting part, as we know, is that the energy that's carried by a wave is proportional to its frequency more than its wavelength. So the higher the frequency, they seem to carry more energy, and they become a little bit more dangerous to us, as we can see. But IR is very useful in helping us work out what's actually in a compound or what's actually in a structure. We can actually see more about the bonding than anything else. Now, the effect on matter of infrared or heat, the fact that the molecules absorb energy. And this causes the bonds inside the molecules to start to stretch. Now, they can stretch symmetrically, in other words, both stretching the same way at the same time. Now, they can stretch lengthways, or they can do a little bit of a wobbling effect. Excuse me. They can do a little bit of wobbling effect, and they can stretch asymmetrically. Now, stretching takes a lot of different forms. You can stretch along the axis of the bond, or you can stretch the atom across the bond, make the bond move like scissoring, if you like. Now, each of these stretches produces a particular pattern of wavelength or frequency of radiations that comes out. And the IR spectra, or spectrophotometer, actually checks on this. Now, if we are very sensible, we would use a double beam. A single beam would just produce the pattern. A double beam would allow us to put a sample in there to compare against. So we'd have a comparative sample. If we had an inkling of what the substance was, we could put it in there and then use the double beam IR to confirm. So it's quite a very good thing. Now, we tend to use on this one, because we're dealing with such small numbers. Now, think about it. We're talking about 400 nanometers, which is rather short, all right? We're talking in that sort of range. So instead of dealing with those numbers, we actually deal with a thing called a wave number. Now, a wave number is essentially the inverse of frequency. And what we can do is we look at where the pattern exists against the wave number. So while we're testing this, we don't test it in only one frequency, or wavelength, if you like, of IR. We test it over a range of wavelengths and produce different things. At different input infrared energies, we actually get different outputs that can be detected. So it's a very interesting process. So you do it over a bit of a pattern. And so we end up with something that looks something like this. And we can see down on the left-hand end, we have about 4,000 is our wave number there, and numbers actually get smaller as we move to the right. Now, the example here we're given is for hexanoic acid. In other words, a straight chain carbon thing, 6 carbons long, single bonds between it, but we've got some interesting bonds. We've got a CO bond, we've got an OH bond, and we have got a C double bond O bond. So if we look at these, we can actually see a pattern. Now, the peak that appears up about 300, or 3,000, 2971, they've got it written down here as, they say it's the OH stretching pattern. In other words, the bond between the oxygen and the hydrogen stretches. So like rubber bands, it goes stretch, then back, and this produces the pattern. Now, we would call this peak a broad peak. All right? The further the peak comes down, we would refer to it as a stronger peak. So if it's only halfway down, it is not as strong as this, let's say the 1721 peak, the C double bond O stretch. We can see almost reaches 100% transmittance. Right, so that goes all the way down. But that is only a narrow peak compared to the other one. Now, if we then go down into the 1400s and below, some people call this the fingerprint region, but there are a heck of a lot of peaks that can appear there, and it can be problematic to try to distinguish between them. I'm hoping the ones you are going to be given are going to rely upon you being able to recognise things around about the 1500 to 4000 wave number. All right, and this should actually allow you to pick some of these obvious ones to look at, to look for, and if you see them, it'll give you some idea of the type of compound you have.